So, there he is. Once again, we're using this formula, compounding m times per year. When t is a variable, that becomes an exponential function, where my output is a and my input is t. Okay, if I'm given all the others. We just did example 11. I want you to try example 12 on your own. Initially put in 1,900 at 2.75% compounding quarterly. And then ask yourself how much will be there in 10 years, how much will be there in 40 years. No, there's those. So same example, or same equation setup that we had earlier. A equals P, 1 plus R over M raised to the MT, because we're compounding M times per year. In this case, the principal was 1,900. The rate of 2.75% is 0.0275. And so the R is 0.0275. Compounding quarterly means 4 times a year. Each quarter, 4 times a year. So the equation I get is that A equals 1,900 times 1 plus 0.0275 divided by 4, all raised to the 4t power. If we're talking about what's going to happen after 10 years, then the amount in this account after 10 years will be whatever we get when I plug in a 10 for t. And if I do the same thing after 40 years, that'll be whatever I get when I plug in a 40 for my t. Okay. Now I wanted to, there we go. Just show you what I'm doing with the calculator. No problem. On that. So let me move that up a little bit. Move it, and move this thing too. Sorry. I repositioned everything yesterday. So this is how I typed it in. You can see the last two lines there. I have math print on my calculator. So when I do an exponent, like if I did 5 to the power 9, it looks like an exponent. If you do not have that, you have to be a little bit careful about how you type it in. If you have the classic mode, you type in 1900 times 1 plus 0.0275 over 4 and put your parentheses. And then you'll hit your exponent key and it'll look like a caret. If I just do 4 times 10, that's not going to be the same thing as what I just typed in. That's going to take the exponent of 4 on whatever inside the parentheses and then multiply the output by 10. That makes sense? It'll do that first. So if you do that, if you have this option, you just need to make sure that you either multiply 4 times 10 in your head and give yourself 40, type in 40, or put parentheses around the 4 and the 10 like that. So that's what we're doing. Again, if you have math print, it's a little bit easier because then everything that looks like an exponent becomes in the exponent. So in this case, I don't have to worry about parentheses because it's inset inside the exponent. But there you go. Basically, $2,499.06 after 10 years. And $5,686.47 after 40 years. By the way, if you wanted to actually look at some interesting numbers and you can play around with these for a long time. In other classes we do. We mess around with the actual values. But I wanted to point out a couple of things. Okay. When you go from like 10 years to 40 years worth of interest, that's a big difference. Okay. Even at something like 5%. That's not a huge growth rate by any means, but at 5%, going from waiting 10 years to waiting 40 years, that's a really big difference. So the time you leave that money in to accumulate interest makes a big deal. That's a big deal. And then obviously the amount you start with is a big deal too. 12,000, so on and so forth. The rate of growth, that's a big deal. Okay. So all of these variables can affect how much you have after. And that's a good thing to think about if you're thinking how or what are the principles of retirement, of funding a retirement account, for instance? Well, if you're trying to fund a retirement account, what do you want to do? You want to get the biggest rate of return you can. That's increasing the R. You want to invest as early as you can, so you increase the time that it allows to compound. And then obviously you want to put in as much as you can afford. That's maximizing the principal. Does that make sense? That's on each contribution to the retirement account. So if you do have a retirement account, people often tell you to start investing early. That's just increasing the time, and then get good rates of return. That's increasing the R. And then put as much as possible. That's increasing the P. So that's it. That's all I want to say. Now, here's another scenario in which we have an exponential function. What if we say we have percentage growth, but instead of compounding m times per year, we're always compounding. So like we compound every second of the day. This is called compounding continually. And if we have some initial amount P, and our growth rate compounds continually for T years, the amount that we'll have after T years is P times E to the RT. R and T are both in the exponents, so again, the common thing is to let T be our variable, and then we get an exponential function. It turns out lots of natural growth happens continually. Like if we're talking about putting bacteria in a petri dish and letting it grow, well, it's going to grow continually. It's not going to wait, every month to grow. It's going to grow all the time. And money can also grow continually as well, but usually banking's more like monthly, quarterly, yearly stuff. So population growth often happens continually, whether it's population of bacteria or population of humans or anything like that. A equals P e to the RT. So let's do an example. Let's pretend we put in $325,000 at a 5.5% growth rate, compounding continually. We want to compute how much is in the account 10 years and how much will be in the account in 40 years. So we're going to put in $325,000. And since we're compounding continually, we'll use A equals E, or excuse me, we'll use E as our base. A equals P times E raised to the RT power. In this case, we're putting in initially 325,000. Our rate is 5.5%. As the decimal, that's 0.055. And we're compounding continue. So since we're compounding continually, we're going to use this instead of the other. Okay. So the equation is going to be 325,000 times e to the 0.055 times t. After 10 years, we just plug in a 10 for t. After 40 years, we just plug in a 40 for t. Remember, this is the e that we showed on the calculator last class period. So that particular e. I like using the second and then ln button because it already has the exponents built in. And so we get that after 10 years, this account will be worth $563,307.23 approximately. Did I get that number? And then if we did after 40 years, we'll do the exact same thing, but swap out the 10 with a 40. And on my calculator, when I have to do this over and over and over, second enter is a good friend. Right? So in that case, after 40 years, we end up with, that's $2,933,129.39 rounded to 2 decimal places. So if you let this money grow over the course of 40 years, it turns into, well, a very big amount eventually. That makes sense. Now, just so that we've seen it once, this is not, if works into the class, you don't have to. We went from 1 plus r over m to the mt, and as m got bigger, that changed to p times e to the rt, right? As m got super, super big. The reason for that is because if you take 1 plus, let's just do 1 over m to the m power, if that value of m gets really, really big, then this actually goes to e, gets closer and closer and closer to e as m gets really, really big. Does that make sense? In Calc 1, you see limit notation. I'm not writing limit notation here. But what we can't do is I can just show you what's going on. 1 plus 1 over, let's put in, I got 7 zeros there. Notice what's happening, right? When you put in a really, really big number for M, you get really close to that value of E. And as you put in bigger and bigger numbers, you're gonna get E. In fact, this is how E is defined. It's defined as the limit of this thing, right? And it just so happens that it's this 2.71828 number. Okay. So that's how E is defined, is as n gets really, really big, what does 1 plus 1 over n to the m power turn into? Oops. Drop that. Again, that part's not important for this class, but I did want to just point it out. In case anybody's wondering. Now, we don't always have to deal with money. Like I said earlier, one of the common applications to continual compounding growth is population growth. I want you to read question or example 14 and try to do that on your own. We've just changed from money to population. So come up with the equation and then project 10 years. And this says project 20 years. So project 10, project 20. All right, so the equation here is A is equal to 45,320. That's your starting amount of people in the city. Times E to the 0.021 times T. Rate is a 2.1% growth rate. If we're looking at what's going to happen after 10 years, if this projection holds up, then we just plug in the 10 into the T. It takes me longer to write it down than it does to actually compute. And I ended up with 55,910.29. Now, for this one, this is talking about a population. Moodle may ask you to round your answer to 2 decimal places. It also may ask to round to the nearest whole number because populations can be just whole numbers, right? But also, this is a projection, so projections can be decimals. Does that make sense? So it's fine for projections to be decimals, but populations can be whole numbers. So just read whatever the question asks for. If it asks round to a couple of decimal places, round to a couple of decimal places. If it asks round to the nearest whole number, then you'd go 55,910. After 20 years, very similar. I ended up with 68,975. Again, 0.30 at that time. 68,975.30 went around in 2 decimal places. That. This is a very common scenario where we have continual compounding growth. So is this one, where we have compounding n times per year. I'm going to always use P and R as the initial amount and the rate of growth, or we'll see later, the rate of decay. But in other books, rather than using P, because P is often associated with principal, they'll use something like A sub 0. That's just the amount at time 0 instead of P. And they'll use a K for their rate of growth because that's a constant. So a lot of times you'll see stuff like this as well. This is just different letters for the same thing. Okay. I like to use P and R, but other times when you look through the book, or if you look through other books, they might use A sub 0 to mean the initial amount, and the rate might be just a K instead of an R. Right? That's a very common thing that happens. But that's basically it. So let's do one more example. A county had a population of 15,800 people in 1980. On average, it has lost 1.5% of population each year. Create an equation for the amount of people in the county T years after 1980, given that the loss or decay rate is compounding continually. And then what would the expected population be in 2005? What would the expected population be in 2040? All right. So we're compounding continually, but there's sort of 2 curveballs here. One of the curveballs is we lost 1.5%. That means when I write my decay rate, or when I write my rate, it's going to be a negative. All right, it's going to be a decay rate, so the rate is going to be negative. So R will be a negative 0.015. We're starting at 1980. So the T of 0 is 1980. If we do that, then our principal, our starting amount, can be 15,800. Our starting amount of people can be 15,800. So as far as the equation goes, pretty straightforward. A equals 15,800 times e to the negative 0.015 times t. We try to find the population in 2005. Since T is the years since 1980, that's going to be a T of 25. Okay. So when I plug that in, I get negative 0.015 times 25 there. We're compounding continually, so it's the equation we're looking for. So 15,800 times e to the negative 0.015 times 25. That gives me a projected population in 2005 as 10,859. And then I'll round it to 2 decimal places, but again, Moodle might have you round to the nearest whole number. I don't know. And if you wanted to, you could go back and check the data, because 2005 obviously was a number of years ago. So you can check and see if the population matched that or if the projection got pretty close. And then if it did, you'd know that maybe the projections are doing well. And then it asks for the population in 2040. That's going to be a projection into the future, but that's going to be a projection with t equals 60. And we ended up with 6,423.80. Notice that because we used a negative R value, you can see that population is declining with the negative R. In our previous examples, we always used positive R values and everything was increasing as we increased the value of t. Here, as we increase the value of t, we're declining. So, any questions about that? So if you have a decay rate, just use a negative R. And oftentimes in these real-world application problems, your t is going to have to start at some year, like 1980. T of 0 is going to be associated with some year like 1980. And then you have to use the correct t value associated with the appropriate year. Okay? So that's it. Those are the two curveballs. Using starting value at some specific year and then decay rate are two different things on this question on example 15. So that's it for section 4.1 and 4.2. For those two sections, that's the whole of what we're covering in those two. Now in section 4.3 and 4.4, we deal with logarithmic functions. So we just got done dealing with exponential functions. We saw two really common exponential functions, one with growth of m times per year, the other with growth that was continually compounding. Now we're going to look at some logarithmic functions. So the first thing we need to understand is, what is a logarithm? What is it telling us? It's actually covered here because of its connection to exponents. Excuse me. So we're going to have a log, and then we're going to have a lower subscript of b. That is what we call log base b. All right. We're going to plug in some value of a and get out another value, which we'll call p. If I wrote that in an exponential way, what that means is a is equal to b raised to the p power. Because of this connection, we call b the base of the logarithm, because it's the base of the exponents expression there. And because we dealt with bases in exponential functions where the base was greater than 0, not equal to 1, we'll do the exact same thing with logarithms. We'll always assume the base of our logs are positive and not 1. 1's the trivial case. So this connection between logarithms and exponential functions turns out to be really nice. I can use the connection, if I want to solve logarithmic equations. If I have log base 3 of x is equal to 2, or if I have log base 7 of 343 is equal to y, or if I have log base b of 16 is equal to 4. Or if I have log base b of 9 to the 6th power is equal to 12. These are all exponential equations that I can solve for the unknown variable by converting into exponential form. All right, see, these are all logarithmic equations. I can solve for the unknown variable by converting into exponent form and then figuring some things out. So like on this one, this is telling me that x is equal to 3 raised to the second power. So we need 9 there. Log base 3 of 9 is equal to 2 because 9 is 3 squared. This one is telling me 343 is equal to 7 raised to the power of y. Now, in this particular case, it works out nicely because 7 raised to a whole number is 343. If you don't know, 343 is 7 raised to the third power. Now we're going to get things where we don't have this nice connection. We'll have to see what's going on in those cases later. But in this case, it turned out really nice. In this particular case, it turned out really nice. And therefore, the exponents have to be equal, and y has to be equal to 3. In this case, we would say 16 is equal to b raised to the 4th power. And so we're thinking, what can I raise to the 4th power to get a 16? I could take a 4th root of both sides if I wanted to. Or I could just realize that 16 is 2 raised to the 4th power. So that means the base has to be 2. Everybody okay with that? This is going to be one of the key things about solving exponential equations. If the bases are equal, then I can set the exponents equal. If the exponents are equal, then I can set the bases equal. This is a little bit tricky. We have 9 raised to the 6th power is equal to b raised to the 12th power if I write that in exponential form. This one I have to manipulate a little bit. 9 is 3 squared. So I have 3 squared being raised to the 6th power. But if you know the rules of exponents, there's a power rule of exponents that says if I take 3 squared and raise that to the 6th power, that's actually 3 to the 2 times 6, which is 3 to the 12th power. Right, know that rule of exponents? It's called the power rule of exponents. You raise something to a power, you can multiply the exponents. So in this case, b is 3. By the way, hopefully we see that's probably not always going to work out nice. You know, what if I had 37 instead of 9 to the 6th? 37 is something raised to the 12th power. That'd be a little bit tougher. I'd have to use a 12th root. I could still solve this, but I'd have to use 12th roots, and I get some ugly numbers. Okay. And we will get some ugly numbers in just a moment. Now, there are 2 very common bases for logarithms that we use very, very often. One is base 10. Sometimes base 10 is called the common log. And then the other is base e, which is referred to as the natural log. If I have log base 10 of x, notationally what people do, if it's base 10, they just leave off the actual 10. Right? That's the only number. If you see log without a subscript for the base, you assume that the base is 10. So it's the common log. Right? And if you have a logarithm base e, that's written as ln of x. That's the natural log. Some people ask, well, why is it just NL instead of LN? Because not every language do you have, when you say natural log, you put the natural in front of the log. So most Latin-based language use logarithm natural, right? That's what it would be. So ln is what we get. ln is the common, or excuse me, it's the natural log base e. And we can figure things out. If we wanted to calculate with the natural log, and if we wanted to calculate with the common log, or log base 10. We go ahead and do these. So I have all these problems written down. If I want to do natural log of x is equal to 5.4, that means x is equal to e raised to the 5.4 power. That's something that I can plug into my calculator. It's going to give me some irrational number of 221.41 approximately. If I do natural log of e to the 23 is equal to some value, let's call it y. This is saying e to the 23 is, this is base e, so e to the y power, just like we had before, we get y is 23. Very similar to the previous things, right? This tells me x is equal to base 10 raised to the third power. When you do that calculation, that's 1,000. So log base 10 of 1,000 is equal to 3. Because 10 to the third is 1,000. Now here's where things get a little bit sticky. We have 1,025 is equal to 10 raised to the z power. If I rewrite that as an exponential. Okay. And we'd ask, well, what power do you raise? What power do you put on a 10 to get 1025? Turns out it's not a nice number. It's not going to be a nice whole number. Okay. We just saw that 10 to the third is 1,000. 10 to the fourth would be 10,000, by the way. So it's probably going to be 10 to a power. That power is going to be probably just a little bit over 3. So if we didn't have technology, we'd be kind of stuck here saying that it's going to be a little bit over 3, and then we could guess and check some, how close to 3 it's going to be. You could hone in on that if you wanted to. But the nice thing is we do have technology. We have our calculator, and our calculator can do those types of calculations. It can take the log base 10 of 1025. In fact, it could have done this calculation as well, if we wanted to. And we can confirm our answer over here as well. And we can confirm our answer with the other one as well. So let me project that. Project the calculator up there. On the TI-84, we have our natural log button right here. That's the ln. And then this log is log base 10. You can see that when you hit second in the number, you get e to the x. Second, and then, not the number, second and then ln, you get e to the x. Second and log, you get 10 to the x because of the connection there. So, there you go. Earlier, I found out that natural log of 221.41 was going to be about 5.4. And so if I just hit that natural log button and then put in that number, I should get 5.4. Okay, and sure enough, I do. Earlier, we saw that natural log of e to the 23rd was 23. We can confirm that now. Earlier, we saw that log base 10, or the common log of 1,000, was going to give me out 3. We can confirm that as well. Now, if we want to find log base 10 of 1025, I just do log base 10, 1025. And sure enough, I get a little bit over 3. Okay. If I rounded this to 2 decimal places, it'd be 3.01. So without having to write down the exponential form, I can just now say, well, I know how to calculate log base 10 of any number using my calculator, and natural log of any number using my calculator. So that's what we just see. The calculator has log base 10 and the natural log, and then we can calculate any number we want. We already did the first 2. By the way, you can do natural log of 45. That's going to give you some irrational number. Instead, I want you to just type in log of 1 over 1025 on your calculator. Log base 10, 1 over 1025. What you end up with, since the argument was the reciprocal of 1025, we get the negative of 3.01. Does that make sense? Log is giving you exponents. So if I'm putting in reciprocals, I get the negative of what I put in previously. Because that's how negative exponents work. Now, if we have other bases, you can rewrite this as exponentials sometimes. And that first one, you can rewrite that as an exponential. Second one, it's going to be hard to do by writing exponentials. So if we have other bases, we will be able to calculate those logarithms a little bit later. Okay. I'll show you a couple of different tools to calculate with those logarithms, with log base 6, log base 2, log base anything we want, as long as the base is bigger than 0, not equal to 1. Okay. So later on, we'll calculate with other bases, but right now, we have log base 10 and natural log on our calculator. Okay. Now, I want to point out something. When we did natural log of e to the 23rd power, we got out at 23, right? Got out at 23. What if I did that in reverse? What if I did e to the natural log of 23 as its exponent? And then I'll do that 10 to the log of 5.2 is the exponent. And then we'll guess at 6 log base 6 of 4. Go ahead and type this one in, and then type this one in. Okay. I should have done this. So we already found that natural log of e to the 23rd power was 23. Okay. If you type this in, e raised to the natural log of 23 power, you will also get, or you should also get 23 if you typed it in correctly. If I do that with base 10, it's going to work the same way. Log of 10 raised to the 5.2, where 10 raised to the 5.2 is all in the argument of the log, gives me a 5.2. And then if I take 10 raised to the log of 5.2 power, I get 5.2. What do you think is going to happen when we do that same process with base 6? Well, we're going to get the same thing, right? Same principles. If I did log base 6 of 6 to the 4th, I get 4. If I do 6 to the power log base 6 of 4, I get 4. By the way, we can see this very easily if we rewrite this thing in exponent form, right? In exponent form, this is saying 6 to the 4th is equal to 6 to what power? So what power would I have to raise 6 to get 6 to the 4th? You say, well, it's obviously 4, right? The other way is a little bit harder to comprehend. This log base 6 of 4 is equal to, this is the power of 6 needed to give out a 4, to produce a 4. Does that make sense? So this whole thing, if I call this log base 6 of 4, let's call it a letter, I'll call it W. This means that 4 is equal to 6 to the W power. Okay. Well, again, this thing's just the W. And I know 6 to the W is 4, so that's 4. It's the power you need to get out of 4. So it has to be that one. Okay, follow? Now, what I'm getting at is that exponents and logarithms can cancel each other out when I have same bases, right? And that's going to be a really big deal when we solve exponential equations and we solve logarithmic equations. That exponents and logs work in this inverse way. That logarithms work as the inverse of exponents. Yeah.
How do you type like log base 6 on the calculator? Only just log 10.
Well, we haven't gotten to that yet. I will get to that though. But so I was just thinking through it here, but so I'm showing you that it has to work this way, but in just a little bit, we'll see how to do log base 6 on the calculator. And we'll see how to do log base whatever we want on the calculator, as long as the base is bigger than 0, not equal to 1. But we will in just a moment, in just a little while. Okay. So this is what I'm getting at. This is one of the really nice properties of logarithms and why logs and exponents, exponential functions and logarithmic functions are studied at the same time. Because they, in some sense, undo each other. If I take log base b of b to a power, I get back the power. If I take b raised to the log base b of p, I get back the p. Okay. In general, with any base, bigger than 1, not equal, bigger than 0, not equal to 1. So with any nice base, I get that property. And that's regardless of what that value of p is. Whatever the value of p is, I get that. Okay. Now, before we do more calculations, I want to do a little bit of graphing with our base log functions. All right. We'll look at the graph of like natural log of x. We'll look at log base, various things. So we'll start graphing. And what we'll see is that with these base log functions, the domain will be from 0 to infinity. The range will be all real numbers. and we'll have an asymptote at x equals 0. Let's take f of x is equal to log base 2 of x. Right? So log base 2 of x has this graph. Notice that we have an asymptote at x equals 0, that vertical line. As we move to the right, it shoots up. As we move to the left, we shoot down towards negative infinity as we get closer to x equals 0. Now, the reason it looks like this is because of its connection to exponents. I said logarithms undo exponentials. If you look at the graph of an exponential function, y equals 2 raised to the x power, it's doing things like going through 0, 1. It also goes through 1, 2. Notice what the log function does. It goes through 1, 0 and 2, 1. So we're exchanging the roles of x and y there. Everybody get that? So these, in some sense, are inverse functions of each other if we restrict the domain properly. All right. So all of the properties we got with our base exponential functions, now we're getting in reverse, meaning the x and y haven't changed, with logarithmic functions. So with our exponential functions, the domain was all real numbers. Now the range is all real numbers with logarithm functions. With exponential functions, our range were all positive values. Now our domain is all positive values. Is that okay? And if you think about it, there's a pretty obvious reason why. If I have a function like log base 2 of x, if I have that function, if I try to plug in a 0 or a negative number, this is asking what exponent do I raise y to do I put as the power of 2, I'll call that exponent y, to get a 0. And you'd say, well, there's no chance that you raise 2 to a power and get a 0, right? There's nothing that would give you 0. So this does not exist. And the same thing is true if you have any negative number. Let's take a negative 4. Plug in log base 2 of negative 4. That also does not exist. Because it's asking you what power do I raise 2 to give me a negative 4. And you'd say, well, 2 raised to any power would be a positive. So there's nothing that you can raise and get a negative 4. Okay, follow that? So the domain has to be all positive values because of the way logarithms are connected to exponents. And as long as our base is positive, then our domain is going to be all positive numbers. By the way, let me just plot some points. Notice again, 2, 1 is a point. Notice that 4, 2 is a point. And notice that 8, 3 is a point on this graph. Because 2 raised to the first power is 2. 2 raised to the second power is 4. 2 raised to the third power is 8. Oh, I gotta put the commas in there. Sorry. I'll highlight them. And then if you did like 16, 4, that would also be a point on this graph. Because 2 raised to the fourth power is 16. Now, if we do natural log, we get a very similar shape. But as you can see, as you move to the right, while it grows forever, it grows at a slower pace than log base 2 because our base is bigger. If our base is bigger, then we're growing at a slower pace. Okay. Does everybody understand that? It's the inverse of exponents. If our base is bigger on the exponent, we grow really fast. But now we're going slower because it's reversing the roles of X and Y. By the way, if we did log base, let's do a 0.5. Notice that's just a flip across the x-axis of log base 2. Just like when we took base in our exponential functions, base 2 versus base 1/2. One of them was growth, one of them was decay. Now it's the same thing. One of them's growth, one of them's decay. One of them gets bigger, one of them gets smaller. Any questions about that? Straight. Good. So that's what these graphs look like. And the properties of those graphs. Now, as always, from our base logarithmic function, we can shift left and right by swapping the x out with an x minus h. And then we can vertically shift up and down by adding a k at the very end. Okay, and if k is positive, it moves up. K is negative, it moves down. If h is positive, it moves to the right. If h is negative, it moves to the left. That's with x minus h as our value there. So we can do the same thing. We can vertically shift. We can horizontally shift. We can also do a horizontal stretch or shrink by a factor of b. We can do a vertical stretch or shrink by a factor of a. So that's the standard transformations, right? All the standard transformations we can do. If A is negative, then it's a flip across the x-axis. If B is negative, flip across the y-axis, cetera, et cetera. So we can do all the transformations to our base log function. Okay. So I'm just going to kind of talk through these. For g of x, we have a log of base 3. We have an x plus 5 inside the argument of the log. That means we're going to shift left 5 units. We have a minus 9 on the outside. That's going to be a downshift of 9 units. And we have a 2 out in front. That's going to be a vertical stretch by a factor of 2. I won't draw that because you can, once we use log base 3 on the calculator, we can graph that on the calculator. Perfectly fine. So you can graph that on the calculator if you want, once we've seen log of different bases. H of x is natural log of 2 times x plus 4. That's a horizontal stretch shrink by a factor of 2. Technically, it's going to be a shrink by a factor of 2. And then plus 4 is going to be a vertical shift up 4 units from our base natural log function. And again, you can type that on your calculator and confirm that as well. Okay. Now, the one thing I do want to confirm on these is the asymptotes. Remember, we have a vertical asymptote at x equals 0 on our base function. So if we shift our base function 5 units to the left and then down 9 units, where is that asymptote now going to be? Well, the shift left 5 units just shifts the asymptote left 5 units as well. So that's all we have to do. We can say, oh, it's shifted left 5 units, x equals -5 would be my vertical asymptote. You can always figure that out by just saying, what do I plug in for x to get a 0 in the argument of the logarithm? In this case, you plug in -5, you get log base 3 of 0. So there, that's where you have your vertical asymptote. So on g of x, we'd have an asymptote at x equals -5. For h of x, we're not shifted left or right at all. So we still have our asymptote at x equals 0. Does that make sense? Is that pretty easy? Asymptote just shifts with the x. So okay. Other things we can do with logarithmic functions, we can find x-intercepts, find y-intercepts by plugging in y to 0 and x to 0. Just as a note, before we do the algebraic calculations, so like I said earlier, if you shift it left 5 units, you get shifted left 5. But I want to point out that with these logarithmic functions, we're always going to have one x-intercept. Going to cross the x-axis somewhere. But we're not always going to have a y-intercept. Notice that the base 3 function has no y-intercept because that's where the asymptote is. Asymptote is at the y-axis. And if you think about shifting it over 2 units to the right, you're never going to cross the y-axis. So these logarithmic functions often won't have a y-intercept, but they will have an x-intercept. Okay. Even if we've shifted down like 9 units, we will eventually have an x-intercept. It's just going to be way, way out there. Does that make sense? You have to go way, 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 way out. And eventually, maybe at 5,000. Oh, still under 5,000. Didn't know this, but maybe it's 45,000. Maybe at 50,000, we've crossed over. Yep, at 50,000, we've definitely crossed over. So as you can see, as you move out, we still are growing all the time, but just slower and slower and slower. Okay. So just slower and slower and slower all the time. So eventually you will cross the x-axis no matter what. So let's do that with these two functions. Let's take g of x equals log base 4 of x plus 3 minus 4. And h of x, that is the natural log of x minus 2 plus 2.2. We'll find the x and y intercepts if they exist. Well, x-intercept will. If the y-intercept exists, we'll find that. And then we'll also find the asymptote. We know there's going to be an x-intercept, so I'll start with that. Okay. X-intercept, as always, we plug in the y value of 0 and then solve this equation. Adding 4 to both sides gives me 4 is equal to log base 4 of x plus 3. And then what I do is I rewrite this as an exponential piece. I see, because of what we dealt with earlier, this x plus 3 has to be my base raised to the 4th power. That's going to be a pretty big number. That's fine. 256. And then I'd subtract 3 from both sides, giving me x is equal to 253. So my x-intercept is 253, 0. That's where this function crosses the x-axis. Now let's look for the y-intercept. We plug in 0 for x. And we get that. By the way, log base 4 of 3 is a real number. It's going to be some number. It's going to be irrational. It's going to be messy. But it is a real number. And so that is the y value of the y-intercept. Now again, in a little bit, hopefully today, maybe if not today, then definitely the next time. Well, I'll show you how to get an approximation of that just using calculators. Type it into your calculator. But for right now, that's the y value of the y-intercept. So we have the y-intercept 0, comma, whatever this number is. By the way, we could have recognized that we were going to get a y-intercept because with this transformation, it's a shift left of 3 units. And if I shift it left 3 units, then I will cross the y-axis. So the vertical asymptote is the asymptote x equals -3. On this, that's just a shift left to 3 units. Think of it as x minus h. So minus a -3 gives me a +3. Let's do the same thing for h of x. If I do the same thing for h of x, what I get is a y value of 0. When I'm finding the x-intercept. If I subtract 2.2 from both sides, I get -2.2 is equal to the natural log of x minus 2. Then I rewrite this in exponential form. This means that x minus 2 is equal to e raised to the -2.2 power. By the way, I can do that. I can raise e to a negative power. That's not a big deal. And then I would add 2 to both sides. So the x value is going to be e raised to the -2.2 power plus 2. That's going to give you some real number, and we can get a decimal version of that if we want to by just typing it into our calculator. I'm going to leave it as is, and I'm just going to say that means that the x-intercept is the point whose x value is e to the -2.2 power plus 2, and whose y value is 0. Again, on Moodle, you'll be asked to just round that to a couple decimal places.
Moodle, like how we did the other one, like the log base 4 3 -4.
That would be
Just
rounded.
rounded.
Yep, that would be rounded too. Yep, and for a couple of decimal places. And again, I haven't gotten the base 4s and 6s and all that stuff yet, but I will. I will very shortly here. But The y-intercept, we plug in x equals 0. So h of 0, that's going to give you the y value is natural log of 0 minus 2. Plus 2.2. And here's where things go a little bit off the rails. Natural log of a negative number that does not exist. That's the undefined that we were talking about earlier. The domain of a logarithm, like the numbers I can plug into any log, have to be positive because we're saying e to what power is negative 2. You say there's no way I can get a negative if I take a positive number and multiply it times itself. So this is the undefined. Or does not exist, however you'd like to say that. Because we have a negative inside of the natural log. So this means that there is no y-intercept, or that the y-intercept does not exist as well. We could have also seen that and thought through that logically, because the vertical asymptote was x is equal to a positive 2. Right? X minus 2. X was equal to a positive 2. So if the vertical asymptote is at x equals positive 2, and I'm getting some type of shape like this, then I know it's never going to cross the y-axis. That's true. So this is the situation we don't get a y-intercept, because this is a log shifted right. Any questions about x-intercepts, y-intercepts? Like that? No. Is that pretty easy? All right, then I won't do the example 8. Example 8 was the last example. That was on shifts. So that's all of 4.3 and 4.4. 4.3 and 4.4 is about graphing logs. Figuring out how they work, what their connection to exponents are. And then, once we understand the connections between logarithms and exponents, then we can find some log properties. We can look at some logarithmic properties. These are all going to come from this. All going to come from the connection between the logarithmic equation and the exponent equation. Whenever you're looking at logs, you're really looking at powers of the exponents. The logs are like the powers of the exponents. So the way they behave is going to be slightly different than like how polynomials behave. So let's start out with some basic facts. If I take log base b of argument b to the p power, I get p. We actually saw that earlier, right? We took natural log of e to the 23 and we got a 23. And we said, yeah, that had to be so because we're asking what power do you raise e to get e to the 23? It's obviously 23. So what power do you raise b to get b to the p? You get p P. Okay. That also means since if you just plug in a B, you get B to the first power, right? That's an omitted 1 exponent. Log base B of B has to be 1. And because any positive number raised to the 0 exponent has to be 1, log base B of 1 is the same thing as log base B of B to the 0th power, which is going to be 0. This is like saying that when you plug in the exponent to 0, you get out a 1. That works for any base as long as the base is positive and ours is positive. So one property of logarithms is that if I have the same base, log base B of B to a power just gives me out the exponent. Okay. So we can very quickly just look at these and say if I want to do log base 3 of 3 to the 7th power, that's got to be a 7. Log base 2 of 8 raised to the 6th power. I'll rewrite that in just a second. I'll write down all the others. So log base B of 3 to the 7th is just 7. Log base 2 of 8 to the 6th power, I want to think of 8 as 2 raised to the 3rd power. Is that okay? Everybody okay with knowing 8 is 2 to the 3rd power? And then my power rule of the exponents says that's log base 2 of 2 to the 18th power. And then that property tells me that's going to be 18. And the property I just looked at tells me that's 18. Natural log of e to the 5th, since natural log is base e, I just get 5. Log base 9 of 1. Again, the way we think of that is 1 is 9 to the 0th power. So I get 0. Usually I don't make that intermediate. Is that all right? So that's the same rule we kind of looked at earlier today. Okay. The other rule we looked at earlier today was, so we had this is the rule we just said, was that if I take e raised to the log base b of x, I get back x as well. Now I do have to worry a little bit about what x is, because remember you can't take log of a negative number. So in that second equation, if I used a negative number, it wouldn't be true. So long as that x is a positive number, the second equation is true. So I do have to worry a little bit about domain there. Well, I'm just gonna talk through this slide. So notice that if I take natural log of e to the 12th, I'm just gonna get 12. If I take e to the natural log of 4.85, I just get 4.85. The third one is the trick one. The third one is it does not exist because you can't put a negative inside of a log in the argument of a log. But the fourth one there, 7 raised to the log base 7 of 5.9 is going to be 5.9. Okay. So again, natural logs and e to a power cancel out and you just get the power. E to a power and natural log cancel out and just get the argument of log. And that works with every single base, not just base e. I don't have this yet. Now, here's the weird rule that people often have a hard time with natural log. So this is the product rule for logarithms. So if we have a log base b, and inside the argument we are multiplying m times n, then what it is, in another version, is log of m plus log of n. This is called the product rule for logarithms because of the connection to the product rule for exponents. So I'm going to kind of explain where this comes from and then talk through it. So we have this exponent rule that says when I take the same bases with different exponents, when I multiply those two numbers together, I can simply take one base and then add the exponents up. It's like saying I take b to the third times b to the fourth, and that gives me 7 factors of b, right? 3 factors times 4 factors gives me 7 factors. So that's the rule that I'm using. Okay. The log rule says if I take log base b of m times n, I do log base b of m plus log base b of n. In this equation, we can think of m as being b raised to the x power, and think of n being b raised to the y power. What we're saying is that the log base b of b to the x times b to the y, we know based on this rule, this is log base b of x plus y, right? So I'm getting x plus y. And just go through this, what's x? Well, x is log base b of b to the x. Y is the same thing as log base b of b to the y power. So again, this is log base b of n plus log base b of n. Okay, see that? So we're saying log base b. On this side, this is m times n. On that side, log base b m plus log base b n. Make sense? So this is the logarithmic version of the product rule of exponents. That's all I'm getting at. But it's really difficult for most people because a lot of times we think of polynomials. And if we have polynomial multiplication, then it doesn't turn into an addition problem, right? At least not add it, it's not the same thing as adding something. But logs of the product is equal to the sum of the individual logs. And all of the exponent rules are going to have versions of rules with our logs. We have a quotient rule for logarithms that comes from our quotient rule for exponents. Remember the quotient rule for exponents is that b to the x divided by b to the y is b to the x minus y. Like if I took b to the 7th divided by b to the 3rd, I'd get b to the 4th. Since I subtract the exponents. Well, that's the same thing here. So we just change our multiplication to a division, and that swaps multiplication with, multiplication changes to division. We do m divided by n inside the argument of log b. And then on the right-hand side, it'll be log base b of m minus log base b of n. That's the quotient rule for logarithms. Again, this is always assuming we have nice values for our b, our m, and our n. So as long as all those things are positive, we're good to go. Here's the product rule for logarithms. This one says log base b of m to the power p is the same thing as p times log base b of m. Let me explain where this one comes from. This one comes from just the product rule of exponents. The product rule says, not product, the power rule of exponents, I apologize. Power rule for exponents says if I take b raised to the x power and I raise that whole number to the power of y, that entire number to the power of y, then that is b to the x times y power. That's the power rule of exponents. Okay. So power rule of exponents is this. If I let m be b to the x power, now take log base b of b to the x raised to, I'll call it the p power instead of the y, because my rule, the way I wrote it on the slide, said p instead of y. That's just m to the p power. That's log base b of b to the x times p, or p times x, doesn't matter which way you write it, which is p times x, which is p times the log base b of b to the x. There you go. So what's that mean if I let m equal b to the x? That means the log base b of m to any power is equal to p times the log base b of m. So any exponent can be brought out front. Now, I just want to point out before we move on how great of a rule that is when solving exponential equations. How great of a tool we have here, right? If I have an exponent which has a variable in it, like if I took 3 raised to the x power, if I apply, let's say, natural log to that, this tool allows me to take this exponent out front and create x times natural log of 3. And that's just a real number. And so now I've turned any exponential expression, if I apply log to it, this is just a linear expression. It's just x times a number, coefficient times number, or excuse me, coefficient times variable, variable times this number. So that's a very, very important tool that we'll have when we solve exponential equations, logarithmic equations next week. But for now, I'll just leave it as that. Okay. Now, before I'm skipping some examples that we'll do at the beginning of next week. So, beginning of next week on Tuesday, we'll use these tools to calculate some specific values and rewrite things and so on and so forth. But before we leave, I want to talk about how to actually calculate with our calculator something like a log base 7 of a number. So the rule that we're going to use, I'll show you 2 ways to do it with the calculator. All right. But one of the rules we can use to calculate a log base 7 of a number is a change of base rule. The change of base rule says if I take log base b of x, that is going to be the log base a of x divided by the log base a of b. Okay. A and B are bases that are both above 0. X can be any value, as long as obviously it's above 0. Otherwise, it doesn't exist. Technically, you don't have to have non-exist here. You don't have to force X to be greater than 0, because the left and right hand side both don't exist if X is negative or 0. There. So this is a change of base rule. And this allows us to calculate things like log base 3 of 14 and log base 7 of 90. And log base 7 of 0.5. And why that allows me to do that is because my calculator has the common log and the natural log on it. So what I would do using the change of base rule to calculate this first one is I would either take the natural log of 14 and divide it by the natural log of 3. Or you could take log base 10 of 14 divided by log base 10 of 3. Notice that it doesn't matter what the A is, right? You could use base E, you could use base 10. But our calculator has natural log, our calculator has log base 10. So let's plug that in. I'm going to take natural log of 14 and divide it by natural log of 3. When I do that, I get about 2.4 of them. By the way, if somebody else took log base 10 of 14 and divided it by log base 10 of 3, they would also get 2.4 of exact same numbers. And this means that if I take 3 to the roughly 2.40 power, I'll get about 14. Okay. On your calculator, you could just say 3 raised to the power of your answer, and you should end up with 14. Obviously, when I wrote it on the board, I had to round to a couple of decimal places.
What's the difference of doing it that way opposed to plugging in like just the actual base?
Yeah, I'll get to that in a second. Yep. So that's where I was going next with it. So change of base rule historically has been the one used because a lot of times calculators don't always have these other bases. Okay. Turns out if you have the TI-84, your calculator also has these other bases. So I'll get to showing you that in just a moment too. Okay. So change of base rule, again, you can either use log base 10 or log base E, natural log. But we're going to do log of 90 divided by log of 7. And that's about 2.31. Here, we take log or natural log of 0.5 divided by that same log base of 7. We should end up, in this case, with a negative value. And that's negative 0.82. Okay. Now, like I was saying, so historically, this is always the way that was done. Because historically, people didn't have computing power, so they had to look up everything. using log base, all of these rough numbers using log base 10 or natural log. And it used to be on a big spreadsheet. Now with a little bit of computing power, our TI-84 has log base 7, log base 3, log base whatever, all built in. So if you wanted to, you could actually use that feature of the calculator to get these numbers as well. Okay, so like the last two examples I did log 90 over log 7. That was log base 7 of 90. If you go into the math menu, oh, I forgot where it's at now.
It's in the first one. You just gotta go down to A.
I missed it. I looked at it. Oh, there we go. Yeah, A, sorry. So in math menu, and then it'll say log base. If you have math print, it does this. It gives you like the underneath number, the base number that you can put in, and it puts it in the right spot. And sure enough, you get that 2.31 again. And if you do the same thing, oh, there. I need to go up first. With 0.5. Oops. Oh, that's why I screwed up. I didn't write the right thing, did I? I should have said natural log 0.5 divided by natural and stuff. Yeah, negative 0.36. I had the wrong number on that last one, didn't I? So on that last one, it should have been a negative 0.36. The log base 7 of 0.5, negative 0.36. So you can use that feature as well if you have logs of other bases. Okay, so you can either use change of base formula, or you can use the log base in the math menu on the TI-84. Make sense? Either of those is fine if you have to calculate something and get an approximate value. Okay. By the way, when you do that, you can even use bases that are like 1.05. They don't have to be whole numbers. I know we've used whole numbers a lot, but we can even have bases of 1.05. And you can either use the change of base rule or just use your calculator to do these. So if I do that on my calculator, log base 1.05 of 2 comes out to about 14.21. And log base 1.05 of 0.12 comes out to about negative 43.46. Again, I'm just typing these things into my calculator, either by change of base rule or by that calculator function where I input my base. This makes sense? Gist of it. Okay. So we can calculate directly using our calculator. We can also calculate using change of base rule. That's all I'm getting at. All right. So like I said, we've given a bunch of log rules. We talked about the product rule, the quotient rule, the power rule. Those are the three most important. along with our, basic rules here, standard rules. And we'll use those next time. So next class period, we'll use those to rewrite expressions and to evaluate some expressions. So other than that, make sure you get the homework done by Friday, tomorrow at 5. One thing I want to point out is that as far as due dates go, while 4.1 and 4.2 are due tomorrow at 5, 4.3 and 4.4 are not due tomorrow, but you have all the tools to do those. Okay. And then we're well into 4.5 right now. Most of the way down to 4.5. All right. Other than that, I'll see you on Tuesday.